So it's my big pleasure to announce today's seminar, acoustic seminar. And the speaker is our PhD graduate, Ivan Toftul, so many of you should know him well. Ivan is now currently a researcher in Canberra in the group of Yuri Kivshak. And since he started during his PhD, and now he continues the topic of optical forces, and they're merging them with acoustic forces, and how all this relates. So probably today we will hear the essence and deeps in their physics, what is common and what is different. Vanya, please, the stage is yours.
Such long introduction, we should drink something. It was, thank you. So yeah, thank you for the introduction. I do have an experience with optical forces, but this time I'll focus only on the acoustic ones. So not all the work, of course, done only by me. It's a group of people, mainly with Kostya Blyoch, Misha Petrov, Yuri Kivshar, Misha Lapin. There's Paco Rodriguez Fortuna and Sebastian Golat. This is, I guess, the main contributors to the papers which contributed to this talk. So some background for the people who don't know me. So I'm a theoretician. So every single experiment you see in this talk is not mine. My main research focus wasn't acoustical forces. So I'm not doing acoustics full time, as I can say. So mostly was doing optical manipulation. So this is my main background. And since you have a hammer as your tool, every problem becomes to be a nail. So it happened to be a very successful way to apply all the methods from optics to acoustics. So I guess our contribution more is a perspective how to see modern acoustics and acoustical manipulation. And finally, I do have a lot of experience with so-called Mie resonances. So when the wavelength is very comparable with the size of the scatterer, it's a rule of thumb when you can hit this volumetric resonance during the scattering. And it's sometimes it's very handy to have in this manipulation techniques. So I will start from the historical introduction. So to the best of my knowledge, this acoustic manipulation, so when you move something with sound, started with the Dvořák experiments in 1878. So he had a speaker, so he didn't have a electronic speaker. So this is how the speaker would look like back in the day. So it's a pitchfork connected to the square resonator. You hit the fork, which is tuned for some specific frequency. Then it radiates acoustic wave. So what kind of acoustic wave we're talking about? During this talk, I will talk only about linear acoustics. And in linear acoustics, we're dealing only with longitudinal waves. So here you can see the oscillations of a small particles of air, liquid, whatever. And you can see this is a plane wave. And important to note here is if you track the movement of single particles, they actually oscillate back and forth, but not moving forward. So there is no mass drift in the linear approximation at all. From that perspective, it's not very obvious that such wave can actually push something because there is no mass flow. But apparently it can. And the experiment that Dvořák did is he took his speaker, then he focused this acoustic wave with his cone, and he had this mill, rotating mill with small pieces of paper. Each small pieces of paper acts as a reflector. And when acoustic wave hits this piece of paper, this acoustic pressure mill starts to rotate. And this was more or less the first experimental, well-developed proof that, yes, indeed, acoustic wave can move things. But the field evolved. So this is fast forward several decades. The most popular scenario of acoustic tweezers and trapping is so-called standing wave, which can be formed by having two speakers next to each other or a speaker and a mirror. And the acoustic wave form a standing wave. And if you put something really small in the standing wave, you can actually trap it. It can be a small piece of styrofoam or a liquid, a drop of liquid, but it cannot go way too big. But for something small, it works really well. And it's actually amazing how people actually evolved using modern consumer electronics. So if you build a phase array of speakers, you can actually move in 3 dimensions. You can rotate the small things by creating local oscillations of the velocity field. Yeah, here's another example of how we can move in 3 dimensions. And the force is relatively strong, so it's for small objects it's much larger than the gravity pull, so it's relatively stable. Another very cool example is the creation of this acoustic volumetric displays. So here you can see a flying butterfly, which is also trapped particles, but it moves very quickly. And by shining light, it looks like a 3-dimensional butterfly. And to have an idea about what is the applicability scales, there is a very nice diagram from this review written by Kishant Halakia and his colleagues, where he compared optical tweezers and acoustical tweezers by the application. And if we take the acoustic tweezers with modern, easily accessible tools and media, so the typical sizes of the particles which you can manipulate, it's usually either tens of micrometers up to several millimeters. So it can be something hard. It can be even some live objects as zebrafish, or whatever you can imagine of this size. So let me go to the fundamental, how we can actually quantify and understand how this works, how these forces work. So let's go back to the plane wave again. And we will need 2 main quantities to describe this wave, which I will operate these quantities later in the talk often. So first one is a pressure, this oscillation of this pressure. And what I mean by this pressure is this addition or subtraction of the pressure relative to the ambient one. And also there is this velocity field. So we can assign a velocity field as like at each point, depending on how local particles move. And the master equations of linear acoustics are very simple. So the velocity is going to be just up to some constant, just a gradient of the pressure. Okay, what's the next step? So again, another demonstration. So we don't have the transfer of mass, but we do have transfer of wave momentum. So the idea is if we put something small here, we expect to see this acoustic pressure force. And this is experimental example. There are numerous examples on YouTube. You can actually just Google like acoustic propulsion or acoustic pressure force. Many people doing this. It's not rocket science. So we have this transfer of wave momentum to matter, but how to describe it properly? So for that, the crucial problem is to solve the scattering problem. So this is the main underlying problem in all the reasoning after. So in every manipulation technique, we always have incident field. It can be standing wave, can be plane wave, can be vortex beam, whatever. Then we have something which scatters that field and produces scattered field. And my claim is by analyzing the scattering problem, by knowing the exact solution of it, it's possible to reconstruct by using conservation laws the force and the torque acting on this scatterer. And by torque, I mean the spinning torque around the center of mass. And in order to do this, we use so-called flux approach. And in order to explain the flux approach, before going to forces, I'll start with absorbed energy, because it's a bit easier to understand, because energy is a scalar quantity, and the flux of scalar quantity is a vector, so it's possible to actually picture it. So first, let's take a look on the left. So if we take a free space, some very complicated wave is going. It has energy flux. And if we take a closed surface, which is marked in red, and if we have nothing inside and the media is not absorbing, so whatever goes in, the same amount of energy goes out. So if we take the surface integral of it, it's going to be 0. However, if you put something inside, and if it's absorbing particle, then there is a change in the energy. So some energy goes in, but the energy which goes out is less. And according to energy conservation law, this energy goes to the particle because it has to conserve. Exactly the same principles apply to the force and torque. Now we need to analyze not the flow of energy, but flow of linear momentum and angular momentum. And since linear momentum is a vector quantity, the flux of vector quantity is tensor. That's why I have a little hat here. But the math is a bit more complicated, but underlying principle is exactly the same. So you calculate the change of the linear momentum during the scattering, you integrate its flux of the surface, and this change will tell you exactly the force which this object is experiencing. And you do the same with the angular momentum flux, and you get the torque. And this is basically the final answer how to calculate forces and torques in acoustics, and basically in any wave scattering problem. It does look complicated if you take a look at the explicit expression for the tensors. It's like a bulky quadratic function of pressure and velocity fields. But it can be simplified in several examples. And one of the first simplification is small particles. And in order to do this, I will employ so-called multipolar decomposition in the scattering problem. So if you remember this figure when we put droplets in this acoustic tweezer, these droplets oscillate with some weird shape. So you can decompose these any oscillations in a series of multiples. Since it's a linear acoustic is a scalar theory, we can operate with a scalar harmonics. And they go as like monopole mode, dipole mode, quadrupole, octupole, etc. But the very good thing about this multipolar decomposition is that if you have a compact particle and it's very small, then it appears that you have only 2 dominant components, only monopole and dipole. All the higher contributions are negligibly small. And it's a very good news. And it's very good news because monopole and dipole radiation patterns are very simple. So this is how the monopole mode looks like. So it's breathing oscillation, and its scattering diagram is radially symmetric. And the dipole mode, which corresponds to the back and forth, small back and forth oscillations, and its scattering diagram also is relatively simple, and it's very easy to describe it analytically. The next crucial step is to introduce so-called polarizabilities. So if we don't have an incident wave, particle does not radiate any multiple. So we introduce so-called polarizability, and let me start explaining the monopole one. So the monopole because it's radially symmetric. It's a scalar quantity. We can assign a scalar quantity to the monopole moment. And it should be proportional to the other scalar quantity in our theory, which is the pressure. So our monopole mode is proportional to the incident pressure and some coefficient of proportionality. This coefficient of proportionality actually hides all the complexity of the particle. And we call it monopole plausibility. And it also depends on the compressibility, because it's about this compression decompression movement. We can do the same for the dipole moment, and dipole moment has direction. It means it's a vector quantity, and it should be proportional to the other vector quantity in our theory, which is the vector field. And so again, our dipole is proportional to some vector field with the coefficient of proportionality being the dipole plausibility. And also it depends on the mass density, the relative mass density of the host medium and then the particle. Because if you have a different mass densities, you have different inertia during these oscillations, and you start to have this out of phase oscillations. That's how you get this dipole radiation pattern. And it's very easy to write explicit scattering fields when you have these moments. And it's possible to take analytically all these fluxus integrals, which looked complicated, but in the end, you're going to have very simple answers. So for example, if we consider this Gaussian beam, which is color-coded in this fancy manner, so this is 2D color map. The saturation means the intensity. So if the field is very small, then it's black. If we have very high intensity, then it's going to be very colorful. And on the other line, there is change of this rainbow colors. It represents the change of the argument, or how phase changes when the wave is traveling. And if you do the math, the answer is very simple. We can distinguish two main contribution. One is so-called gradient force, because it's proportional to the gradient of the acoustic intensity, and importantly, proportional to the real part of the polarizability. Next, we have so-called acoustic pressure force, which actually pushes particle towards the local phase gradient. So it's proportional to this imaginary imaginary part of the polarizability times this combination of gradient and pressure field. And it's possible to show that actually it is proportional to the gradient of the argument of the P. So now, okay, it's very good. We have very general idea how local forces are working on the smaller particles and how to manipulate them. And for example, if we take a second look at the standing wave example, this is how it looked like with our developed theory. So first of all, we consider the standing wave. And first thing to notice is we don't have any phase gradients. So there is no transition between colors. Each node or antinode has only single color. So the pressure force is equal to 0. And it also coincides with our intuitive understanding. If you have two counter-propagating beams, they kind of cancel each other. But then you have this hotspots of intensity, and particles tend to be trapped somewhere in these hotspots. And this is exactly what you usually see in the standing wave trapping experiments. And so the idea of the standing wave trapping found its application in sorting. So if we actually consider monopole and dipole, and we consider the standing wave, and standing wave has different contributions. One is from absolute value of the velocity field, another is absolute value of the pressure field, shown here in green. So you have different position of nodes and antinodes of the velocity part and pressure part of the standing wave. And if you calculate the gradient force, you'll get this prefactor, which is the difference between dipole and monopole pulsability. And it can be negative, it can be positive. Whether it's negative or positive, it depends on the properties of the particle. So for convenience, I distinguish here blue and yellow particles, which have different sign of this coefficient. So then if you make such a sorting mechanism, which is shown on the right, so you have a flow, usually in water, then you have this acoustic wave, standing wave region. You have this separation of this different two types of particles, and then you can sort them out in each subchannel. So this is very typical way of sorting things. But you do need to have this to satisfy this condition of different pulsability signs. So it's not possible to sort using this method any particles. And another avenue is rotation of the particles. So you've seen that on this phase arrays, so there was a moment when particle actually rotated around its own axis. And one of the fruitful example for us was to consider the evanescent wave, which actually has all kind of different components. So you can have an evanescent wave in acoustics. So it decays exponentially. It travels, so the local phase gradient is along this line. And it also have non-zero polarization rotation, so-called spin density. And it's possible to show, and we showed it, that the torque on the small particles, if you put it in such position, actually will correspond to this spin density of acoustic field. So this is an example of calculations. So again, the evanescent wave. And this is animation of the evanescent field total pressure. So this is not absolute value, but instantaneous ones. So you have this propagating evanescent wave. But here in the center, you see the scattering pressure. The scattering pressure, this is basically a dipole radiation, but it rotates in time. So this is for lossy particle. And if you do the math, you can actually check that the torque will be proportional to the cross product of the dipole moment times local value of the velocity field. And if you substitute the dipole moments using polarizability, you can actually arrive that it's proportional to the imaginary part of the polarizability, which in this case identified defined by losses, and this S value. And the S is a spin density. It's not the same spin as a spin in quantum mechanics. It's a purely classical thing. And sometimes it's a bit unusual. Well, what is a spin in acoustics? Like it's longitudinal waves, you cannot have it. And for that, I have another way of demonstrating this. And for example, if you have such geometry, so you have one channel, two cross channels. At first, you put one speaker, you have plane wave, and if you track the trajectory of the particle in the center, it oscillates back and forth, so no circular movements. However, if you put a second speaker and you make a pi/2 phase shift, in the very center, if you track the movement of your particle, it starts to do the circles, because you sum up, because the problem is linear, you just sum up two contributions. So you start to have this circle movements in acoustics, which I call in this presentation spin density. So here's the region of non-zero spin density. And exactly this geometry was realized in 2019. There was relatively simple experiment, but still efficient. So they had two speakers, one speaker and second speaker. They emitted something which is resembled plane wave. They tuned the change of the phase shift such that they had this rotation of the velocity field in the center. They had some meta and they managed to measure this spinning torque and the magnitude was around 0.2 nanonewton per meter, nanonewton meter. It's extremely small, but still non-zero. It was measured, so it was, to my best, to the best of my knowledge, the first observation of this kind of torque and observation of this acoustic spin. What else? So everything what I've discussed regarding the small particles was in the first approximation, where we consider only the monopole and dipole moments, and when the particle is much smaller than the wavelengths. However, there are yes.
Can I ask a question at this moment? So, can we think of, so regarding the acoustic spin, right? It exists. So in terms of velocity, and but indeed it doesn't correspond to any like operator. So it's not an intrinsic property of wave, right? So can we just define it through its torque properties, through its mechanical properties? Can we see that this is a magnitude which defines the rotation of mechanical objects?
So this is exactly the discussion I recently had with
Ivan Fernandez Carbaton?
Unfortunately, not with Ivan, but God, I forgot the name. So yeah, this is exactly the same discussion I had over there, and eventually we could agree that if we define, so it should be measurable, right? Something measurable, and probably defining this spin density is a way of a local field testing and the action on the point particle. This is probably one of the honest way of doing this.
Yeah. I think this is, so this would kind of resolve many discussions or speculations around this, because in the end, this is why we really need it. Yeah, we need it just not to be. This is the first application of it, and of course, we know that if the polarizability will have much more complicated structure, it will be probably not true. But for test structure, test particle, right? It will be true.
So yeah, it's usually how it happens. But when you start to do the math and you arrive to this conclusion, when the torque is proportional to some specific combination of the fields, and it's extremely tempting to name it somehow, and it does have a clear physical meaning in terms of rotation of the velocity vector, and since it's rotation of something, it's spinning of something. That's why it's historically got called spin density. But of course, it's not that it's not intrinsic angular momentum, like it's intrinsic angular momentum of an electron. So it's completely different in that sense.
Something like the Earth.
Any more questions? No?
Yeah. What?
I said that maybe it's like the Earth. That it's also we call it a spin.
Yes. But the spin of Earth is a kind of really a spin of electron. It's not spinning of an electron, right? So this is the difference.
This is the difference, yes.
So yeah.
Will it be the same with different gas, or maybe argon, or just oxide, all this? Will it be the same with different gases? For instance, argon, or maybe in the mountains, or here, or maybe underwater.
Yeah.
It will be the same or not?
Rotation?
Yeah, all this.
Yes, this will be any gas. Yeah.
Yes.
Vacuum, no.
No, I mean acoustics cannot work, almost cannot work in vacuum. It actually There are vacuum forces, but
Okay.
Yes,
Yeah.
yes.
okay, why not?
Mhm.
Yeah, yeah. We had a discussion regarding it. Go on, please.
Yeah, sure.
Can I ask a question? Sorry.
Yeah.
Yeah. Hello, everyone. Nice to see you. I wanted to ask about the spin 2. Can we say here that degeneracy is not broken according to angular momentum in this case? Or is it true?
What do you mean by degeneracy is not broken?
I mean, like in optics, for example, with optical resonator, when we have two angular momentos plus and minus one, and if you apply magnetic field, for example, it will be separated by energy levels.
It is completely disconnected from what I'm talking.
Yeah,
like it's the confusion comes because it's happened to be the two fields using the same words, but there are no energy splitting in that sense here.
that means that if you will change the direction of your, for example, evanescent field, the energy will be the same. Yeah.
The energy of what?
Yeah, but we have
This is the
any.
question.
Okay. There is no any physical characteristics for this.
For example, you can have chiral acoustic particle,
Okay.
and you might have chiral resonances. So you might have different. For example, if you started with a cylinder, you have this degeneracy of vertical and horizontal. Then if you make it if you make a chiral shape of the cylinder somehow, you twist it, then you will start have this degeneracy in terms of the eigenresonant mode of the particle, and you will see it in scattering. So
Yeah.
you have the degeneracy in this case, but if this is connected with not with the field interaction, but rather with a geometrical deformation of the scatterer.
Mm-hmm. But here there is no any agent mode. Yeah.
Not yet. I will mention it a bit further.
Okay. Thank you. Thank you.
Cool. I will continue. So, but by far, I analyzed only the first order in the forces. So the next order is going to be called recoil forces. And the recoil forces are very similar to the rocket principle. And if you have some mass, you throw it away, you tend to move into a different direction. So a very similar thing happens in wave scattering. So for example, there is acoustic Kerker effect. So if you excite simultaneously dipole and monopole modes with specific phases, you can, and you sum up all the velocity fields, you can see that the scattering diagram starts to be extremely asymmetric. So particle radiates a lot to the one direction, but nothing to the other. And if we take only the contribution of the scattering, so the particles putting a lot of momentum in one direction, and according to the momentum conservation law, it pushes itself into the other direction. And to our surprise, so it was known in optics, the mechanical manifestation of the Kerker effect, but not in acoustics. In acoustics, it was overlooked somehow. And when we were studying this, it helped us to describe and to find so-called acoustic lift effect. So how does it work? You have, if you start with anisotropic particle, for example, like ellipsoid, you have acoustic plane wave, which goes from left to the right. But there is a position of this particle where it actually have a stable lift upwards. So it moves forward, but at the same time it goes up. In essence, it's very similar to this sailing. When you have wind, then you put your sail with a right angle, and the speed of your vessel actually goes to the other direction, not collinear with the wind. And in order to achieve this, we need to satisfy two requirements. So first, there should be constant lateral force. And the only way we can achieve it is through these recoil forces. So this scattering diagram and this stable lift position should look something like this. So it should scatter much more to one side, but very little to the other. And also, we should have the stabilizing torque. So the particle should be stable at this position. So whatever small oscillations in rotation, which it might experience, we should have this stabilizing torque, which will rotate the particle back to its inclined position. And surprisingly, we managed to find such parameters of the ellipse, of the ellipsoid. And one of the first our conclusions was, well, if we take it too small, it's not possible. And we managed to show it analytically. It's not possible to achieve it in relay regime when the size is much smaller than the wavelength. So we need to have high order contributions. But when we started to have the scatter bigger, we managed to find this stable lift positions. So here in the plot on the left, so we sweep with the frequencies. Left scale shows the torque. Right y-axis shows the lateral force. And for example, in this example, there are two stable positions. One is S1, second is S2. So where we have non-zero lateral force, but zero torque. And in order to understand whether it's stable or not stable, we need to fix the frequency. For example, if we fix the frequency at point S1, and we'll start to rotate our particle, we'll see that actually, if you go to a smaller or larger angle, you'll always have the torque which wants to restore it to the original position, which is around 45 degrees. But at the same time, the lateral force is non-zero. It always pushes the particle in one direction. It is not guaranteed that you can find it. It's usually a search in the numerous parameters, and Misha Smagin, who's the first co-author in this paper, he managed to find it, and then we're thinking a lot how we can actually explain it. So we managed to find this, and the very logical question, so what? One of the possible applications we could think of is when we try to look at the blood cells. Apparently, so usually you have two types of blood cells. One is leukocytes. Second one is red blood cells, erythrocytes. So leukocytes, they are more or less homogeneous, but erythrocytes, they are anisotropic. So they somehow resemble this ellipsoid shape. And to our big surprise, when we took all the real parameters like density of blood, density of this small blood cells, etc., we managed to find a few stable, well, at least one stable point, which could help realize this sorting of these different blood cells. Probably there are more efficient ways of doing that, but this, I guess, one of the fancy ones. But it's only a theory proposal for now. So the next topic I want to touch is resonant effects. So by far we didn't have any resonances. So we just said that, okay, there is a polarizability, and it's just positive or negative, but it can, each particle during the scattering can have a resonance. It's not important what is the nature of this resonance, but the manifestation in terms of polarizability is more or less clear. When you have a strong resonance, your real part of the pulsability, so it's described by the Lorentz resonance. So the real part of your pulsability will have a change from positive to negative. So if we're speaking about the gradient forces, to the left of the resonance, you're going to, your particle will want to suck into the high intensities, but on the right, on the other side of the resonance, it's actually going to be repelled from the regions of high intensity. And also, another important takeaway here is if you exactly at the resonance, you'll have extremely suppressed gradient force. It's basically, it can be zero. So it's not something like, okay, we should have a resonant particle, do it directly on the resonance, and you should have high force. No, it should be tuned slightly away from the resonance. However, if you want to achieve strong radiation force, then you need to be exactly at the resonance, because exactly at the resonance, so the radiation force is described by the imaginary part of the pulsability, and exactly at the resonance, you will have the maximum enhancement of the radiation force. Wonderful. And how to, we tried to think of some ideas how we can actually use it. And one of the first ones was actually inspired by one concept from optics, where you have this two frequency sorting of particle of different sizes. So let me explain how it usually works. So we remember that on the resonance, the particle experiences very strong pressure force. And then we take two different speakers, slightly tuned. So there is a frequency difference. And we have suspension of particles of different sizes. And depending on the size, we can hit the resonance for one speaker, but not for the other. And it means it will push the particle to one side. But then when another particle with different size come to the sorting region, it will experience the resonance from another speaker and will push to the other side. And so on the right, we consider this parametric map. So we change the size of the particles. Then we have different detuning parameter, so how different the frequency of the two speakers. And the color represents the resulting angle, sorting angle in this scenario. And you can see that smaller particles will go to the right, bigger particles will go to the left. And this is what is visualized on this sorting angle diagram. So this is another way how we can use.
Oh, yeah. At this moment, so what is not very clear, so your particle changes the direction. Mm-hmm. So it's like the trajectory is quite, oh, this is 8K. Oh, I see. This is, I thought this is no. The radius is this, the frequency, right?
Yeah. So the frequency is fixed. You can change the radius only.
Okay, yeah. All right, yeah, sorry.
Mm-hmm. But then it was, I guess, an exercise for a theoretician to describe what kind of resonance we can have. And it's very on time now to speak a little bit about Mie scattering problem, which I guess Misha mentioned yesterday. So the Mie problem is a scattering of plane wave on a sphere of arbitrary radius with arbitrary parameters. And it's possible to solve it analytically. And this is the beauty of this problem, because it gives a lot of insights for spherical objects. So you have your incident wave, then you have your scatter field. You decompose your scatter field into a series of harmonics, scalar harmonics, as we mentioned before, with some weights. And these weights, AN, we call it scattering coefficients. And by applying boundary conditions, it's possible to find the scattering coefficients for the sphere exactly. So we'll have once and for all solve scattering problem for sphere of any radius for plane wave and with any parameters. Then you can write the pressure force, which is proportional to the pressure cross section, and express it in terms of the scattering coefficients an. It's just some combination of those. And then you can just substitute different parameters. For example, this is more or less trivial one. This is air bubble in water. So here on the top, there is pressure cross section. On the bottom, this is the roots. So basically the resonant solutions of the eigenmodes of the sphere. And there is a very big peak next to the first monopole resonance. And it's very clear because there is a very big difference in terms of compressibility of air and liquid. Liquid is almost incompressible compared to liquids, to air. So we have very huge enhancement on this monopole resonance and almost nothing else. But don't pay too much attention to the magnitude of this. It's artifact of our linearity of our theory. When you go to such big enhancement, you will have more nonlinear effects, which will actually decrease the enhancement effects of this monopole resonance. But regardless, the monopole is dominant in this case. However, you can choose different materials. So for example, you can take a sulfur hexafluoride bubble in air, and they have very interesting relative parameters of relative density and compressibility. So it looks very similar to the this very famous plots of mi-scattering in optics for silicon sphere. So you start to have very clear resonances. You can identify different contributions. So for example, this is the blue one is the monopole resonances. The orange one is the dipole ones. And they correspond really well with the eigenmode solutions. So this is the poles of the scattering coefficients. So this resonance would correspond to this one to that one. And the high Q factor, you have the sharp as a resonance you're going to have in transmission. So there is a very nice correspondence between these acoustic resonances and its acoustomechanical manifestation of it.
So, by the way, how about the imaginary parts? So, for the sulfur bubble in air, so for the density and the compressibility, we can have the real number. But how about the imaginary part value? 0.064? Yeah, this is the real one, or just...
Thank you for the question. It's very important to pay attention to. So the imaginary part in this formalism, in these parameters, it's responsible for the losses.
Yes, but how do you find...
It is taken for the real gases.
Okay, I see.
And for the air, the imaginary part for the air is equals to what?
It strongly depends on frequency.
Yes.
Okay. Okay. And yeah, because of so. But you what did you have in mind? So is it like a I don't know, soap bubble with different gas, or you just it's some virtual bubble?
So the virtual bubble is exactly what corresponds to these calculations.
Okay.
What I had in my mind is a soap bubble. Yes.
Oh,
of course, the tension of the soap will bring difference.
But I think tension will not give big contribution. It's more about a lot about pressure as well. Yes. So at least as I understand these. If you take rubber bubbles in water, the tension from the rubber doesn't affect much.
Yes, true.
Okay.
And it's also because of the resonances, they are volume based.
Right, exactly, sure.
So yeah, in this paper, we made a table of several popular materials, and I mentioned typical values of the losses for different frequency ranges. I don't remember by heart, but yeah, I don't remember for which frequency range I took this one. Okay, so yeah, we started to have this multipolar decomposition of the force and the scattering. And for the sphere, it's very easy because you don't have cross coupling between different modes, because sphere is very symmetric. But if you have scattering not on a sphere but on something different, situation is getting more and more complicated. However, you still can do a couple of shortcuts by applying a group theory analysis. So I won't go into the much details, but I'll just mention the brief outlook, how it and why it works. So for example, you start with a resonator, which has some shape. This shape has some symmetries. So it has mirror reflection planes, it has rotational symmetries, it has inversion symmetry. The set of the symmetry operations, which remain the resonator the same, form a group. These groups are usually very well studied, and each group has known irreducible representation. Then you can find the eigenmodes of your structure, and then you can classify each eigenmode by irreducible representation of the resonator, of the corresponding group. Then you can actually say that, okay, for these modes, only these kind of multiples can be in the decomposition. So it gives a rough approximation, like can I have dipole resonance in such shape? Yes or no? Or can I have a monopole resonance in such shape? So it gives you very rough idea of what kind of multiple content you can have in the scattering. But if you go to smaller particles, the manifestation of this analysis is really simple and actually have already been done before, and it's called Willis coupling. So before I mentioned that the dipole is always proportional to the vector quantity to the V, and monopole is proportional to the monopole to the pressure. So in terms of the plausibility tensor, when we write it in this manner, it should be diagonal. But for the bigger particles and for the more complicated shapes, we can have non-diagonal elements. And if you start looking at the different shapes, for example, when you have isotropic sphere, you have only diagonal elements. When you have geometrical anisotropic particle, but with inversion symmetry, you start to have your dipole plausibility as a tensor, but still no diagonal element. But if you start to have bi-anisotropic particles, which are asymmetric, examples are being 3D Helmholtz resonator or just a cone, you start to have this non-zero diagonal elements. So this is now very easily described in this plausibility languages. But it was first discovered by Willis in 1981. And then recently it was revisited several times, at first in scattering by the group of Andrea Lu in 2018. Then in terms of optical forces, and in this Piral paper in 2022. And we also give our small contribution to it when we analyze in terms of this group theory analysis as a particular case of this, of the absence of inversion symmetry. So yeah, it's basically it. I was also wanted to thank all the people who were involved. in this especially in the review and the original works as well. And yeah, this is basically the main papers which I mentioned in this presentation. Thank you.
Thank you.
Thank you, Anya. Thank you very much. Questions from the audience?
We need to look into.
I'm looking into Zoom when there are hands.
Yeah.
Albert Seredin claps. That's local. It is a question. Yeah.
Guys, do you have any question in Zoom? Maybe here.
I
have.
Oh, okay. Please, Jean.
Yeah, okay. You can hear me?
Yeah, I do.
Okay, good. On slide 21, I have several questions. First of all, those momentum forces, etc. Even that one with two speakers. All these forces and momentums, it will be stronger for different gas or no? For instance, in water or in air.
So what is important here is relative value of the compressibility of the particle and the host medium. So of course, if you go from gas to liquid to water, the forces will be drastically different. I cannot say if it's going to be stronger or weaker, because that would depend on what kind of particle do you have.
Okay, then second question. All these vibrations, imagine I don't have a speaker or some source. If I just shake this thing and get the same vibrations, it's possible to get such kind of filtering or no? So I will have some bed that I will just vibrate, or robot hand that will vibrate all this stuff.
Well, I guess if you vibrate with acoustic frequency, you'll actually arrive to exactly the same conclusion.
Sure.
Because basically, your speaker actually vibrates everything quickly.
Yeah, I will put some voice coil actuator underneath. Voice coil actuator, some speaker, but it's lateral one with a rod, and it will vibrate this system.
Yeah, it should work. Like well, you can have, yeah, it should work.
Yeah. Okay. No more questions from me.
There are some questions from Nikita Yurkanov.
Yeah, thank you. I have a very naive question, I think. What's the difference of these applications with acoustic forces, torques, and so on, with the optical ones? I mean, maybe another heating mechanisms because of lasers and so on. Can you comment on this point?
So the main difference is the size of the things you can trap.
And that's all.
Yeah, that's basically it.
Okay.
You do have some more. You do have richer physics with optical tweezers, because electromagnetic waves, the vector waves, and you can have non-zero helicity in your waves. And for example, if you want to do chiral sensing, you can do chiral sensing only in optics. You cannot do chiral sensing in acoustics.
Mm-hmm. That's you told me about spin too, yeah. Like we have no chiral response from particles in the acoustics, yeah.
Yeah, because in acoustics you can have only, so you cannot have isotropic chiral particle in acoustics. Like it's the force on it will be exactly the same as for non-chiral one. Unfortunately, I don't have a proper figure to demonstrate it, but yeah.
Even we cannot construct it, yeah. Like not nature particles, but like meta atoms and so on. Maybe.
Even if you construct it, so actually there is what's the name for it? There is a helicoid particle, which is basically constructed chiral particle for the acoustic waves. And some guys tried to measure different types of forces on it, and they could not find any difference. It was like right spin and left spin.
Yeah.
Yeah, I could send you a bit more on that. It's a very good comment. Unfortunately, I don't have extra slides for that.
Okay. It will be very well to see it. Yeah. Okay. Thank you, Vanya. Thank you.
Any further questions?
Do anyone? Maybe.
Yeah, I still have a lot of questions. For the PR applied work in 2025, yes, because for resonant, the resonance will also generate strong scattering waves. If there's a lot of particles, they will interact with each other.
Yes, it is true. We didn't consider self interaction. So
Yeah,
I guess that function is that not very dense.
Okay, I see.
Yeah.
Okay, thank you.
Okay. Any other question? 1, 2, 3. Okay. I think we can say thank you very much, Vanya, for this grateful speak. So,
Thank you for
if
having me.
we haven't got any question, I think we can end. So, thank you.
Thanks. Very impressive.
Yeah. So,
Okay.
Thank you. Good to see everyone.
Bye.
bye.